You've seen images like this. A spinning top wobbles, so the spinning Earth must wobble. But they always forget to tell you that a gyroscope in space remains fixed due to the conservation of angular momentum. So just what's going on here? Welcome to SetiAstro. So looking at an image like this on face value, it makes sense, right? But here's the big one. A gyroscope spinning like a spinning top on the Earth, that's not in an inertial reference frame. That's in an accelerating reference frame. There's a force being applied to that spinning top or gyroscope, which is causing that precession. The Earth in space is in an inertial reference frame. It's in free fall. So what the heck is causing the tilt to be wobbling? Now let's go ahead and look at a video here from ESA where it's going to show a gyroscope in space and it remains fixed in its orientation while it's in microgravity. Alright, here is a video from ESA in the International Space Station, and you can see with a gyroscope it just remains fixed in the same direction. Even after he rotates the tilt angle, it will remain fixed now in that new position, pointing constantly in one direction. So something has to be happening with the Earth, and we're really going to get into this. It's going to be a longer video. There's a lot going on here as to what the heck is happening with the Earth. So you may want to get a drink and a snack and ready to really probably learn more about the precession of the equinoxes than you've ever thought possible. As always, I made a bunch of code here for the illustrations and animations I got coming up here that go through the actual real calculations for all this. So I'll have a link to this actual script in the video description if you want to work through these or use them yourselves in any discussions you may have. So we need to really find the source of what is torquing the Earth in order to cause it to precess. Right, just like a spinning top on your table, gravity is providing that force to torque that to cause the top to precess. We need to figure out what's torquing the entire planet in order to cause it to precess. And the answer is the moon and the sun. So there are some kind of gnarly equations that are utilized in order to determine this. But let's just start with the basics. The Earth is not a perfect sphere. If it was a perfect sphere, there'd be no torque applied because it's all symmetric, and there'd be no precession. Because the Earth isn't a perfect sphere, it's, this oblate spheroid, it bulges in the middle because of the Earth's rotation. That allows the different sides of the planet closer and farther from both the moon and the sun to experience different torques on them. And the torque is going to be perpendicular to the direction where the moon and the sun is. And I got a little graphic over here. We're going to be looking at essentially the component that's in the up-down direction. Well, the vast majority of the gravitational force from the moon and the sun is off, pointing to the moon and the sun. In fact, it's a huge amount of majority. These angles to the moon and to the sun are very, very small, and we could actually look at them. So here's the actual vector components for the force. The moon's at the bottom. That has a 0.4 degrees difference. So that's represented here. And the angle out towards the sun is this 0.0009. So like 0.001 degrees off. And the moon, we could actually see, that the difference in these angles. But for the sun, to actually zoom in and see the difference in these angles and the torque getting applied to the Earth, it's this component of that total force, that up-down force, is the thing that's torquing the Earth. So between the sun's and the moon's torque on our bulgy planet, that's what's going to be causing it to start to precess. And like I said, the equations for it are a bit gnarly. They're definitely not used to what you've probably seen for normal kind of high school gravity things where there's 2-point masses and you're calculating, like the force between them or something. In particular, the precession really is dominated by the radiance cubed. That's why the near side and far side could have different forces and torquing on the planet. But also this J2 term, and that's something I know most of you haven't heard of. This is the gravitational quadrupole moment of the planet. In high school physics, again, they simplify it all down. Everything's a point mass. Force equals g times mass 1 times mass 2 divided by the radius squared, right? That's not the whole picture. In fact, that's just called the monopole moment of the gravity field. It by far is the biggest contributor, but it's symmetric. And because of that, you're not going to be able to torque on it or do anything. It's this quadrupole moment that actually determines the scale factor of our precession. That's this C minus A in here for the torque, and the actual precession is scaled by Earth's quadrupole moment. And I want to show you that visually if you've never seen it. So here's our Earth with an accurate oblate spheroid size in here. And the vast majority of the gravity field you can see on the left is just the normal gravity field you'd expect for the Earth, right? Just normal, it's a point source. You get closer and closer, the gravity gets stronger and stronger. Here's the actual meters per second squared acceleration, and right down here on the surface is your 9.8 meters per second squared on the surface. And at the top I have the gravity potential equation, and you can see it's the same with the exception now it's 1 minus J2 all this stuff. So if you were to just use the point source, it would just be negative GM over R. But now we have this J2 term, and that J2 term is tiny, like 0.1%. If you get rid of the monopole moment, this is the remaining gravity field. You can see it's not at all like your normal gravity field. There's, if you're just looking at the quadrupole moment, there's both repulsive and attractive areas in there where things would be stretched and squeezed. And the scale here is really small. So even at the surface of the Earth, where you're going to have the biggest quadrupole moment, this is the percent difference from just using the point source calculation. We're talking 0.1 to 0.2% max difference. So 1 to 2 parts in 1,000. That's why you don't talk about it much, especially when you're first learning gravity. It's these higher pole, multipole moments get vanishingly tiny for normal situations. But this little tiny difference has to be there, otherwise there'll be no precession of the tilt of the Earth. And the fun fact here is gravity waves. You've all heard of gravity waves, right? It's the time-varying change of this quadrupole moment that gives rise to gravity waves. Gravity waves are changes in this quadrupole moment of the gravity field, not the monopole, not the dipole, because those are conserved due to conservation of energy and conservation of momentum. The first thing that could actually change in the gravity field and have a time-varying component is the quadrupole moment. So when you hear gravity waves, this weird thing you may not have ever seen before is the thing that's changing, is the thing that's waving. I thought that'd just be a fun thing to let everybody know. When you hear of gravity waves, it's this quadrupole moment that's changing, time varying, spreading across the universe. That's the gravity wave. So going back now to our actual equations on the Earth, we can calculate the averages for the sun and the moon, because they're going to change, right, depending on where the moon is positioned to the Earth, where the sun is positioned to the Earth. But we can calculate the torques on them. The torque from the sun is this 1 times 10 to the 22 newton meters, and the effect from the moon is about 2.5 times 10 to the 22 newton meters, leading to precession rates down here for a total of about 50 arc seconds per year. And if you figure there's 360 degrees in a circle, 60 minutes in a degree, 60 seconds in a minute, and now we're talking 50 arc seconds per year, we can calculate the total precession of the equinoxes to do one full wobble of the Earth, and we got 25,800 years. Kind of this back of the napkin calculation here is very, very, very close if you took the full, more nuanced calculation that factors in a bunch of other things of about 25,700 years. So just with this, we can get the full precession of the equinoxes wobble time frame of 25,800 years just doing this one calculation. I also want to mention these torque values. We're talking, 2.5 times 10 to the 22 Newton meters. So for those of you on the imperial system like I am, you're probably used to hearing foot-pounds. So 1 foot-pound of torque is about 1.3 Newton meters of torque. So they're kind of about the same, definitely the same order of magnitude. 10 to the 22 is a huge number. That is 10 billion trillion Newton meters. So 10 billion trillion foot-pounds of torque that the moon's exerting on the Earth. And you'd think that that's just an absurdly huge amount of torque. Surely that's got to move the Earth more than this 50 arc seconds per year. But the Earth is big. I know we all think, celestially, or Earth being tiny in our brains, but the Earth is big. Like, really big. The amount of angular momentum stored in the planet's rotation is like 10 to the 33 kilogram meter squared per second squared. So you're talking something that has 10 to the 33 units getting torqued by something with 10 to the 22 units. So even 10 billion trillion foot-pounds of torque, it's just not that big compared to how truly huge the Earth is. And there's even more subtlety here, right? As the moon goes around the Earth, how those bulges on the planet are oriented to the moon is going to affect how much the moon can torque on the Earth. And same with the sun. So in blue here is the axial torque from the sun. The orange is the axial torque from the moon on the Earth. And then the green is the combined torque. And you can see not only is it changing over the lunar month cycle, but the torque on the Earth is actually changing over the year as a whole. And we have both positive and negative numbers here. That's just because when the moon or the sun's on one side of the planet, it's trying to torque it up, and when it's on the other side of the planet, it's trying to torque it down. But overall, the direction of torque for that full period is in the same direction. So it's also good to look at the RMS, or the absolute magnitude of this whole torque situation, which really gives us this. So in green here is the total torque that the Earth is experiencing throughout a year. And you can see it's not a constant tug on the planet. It is this monthly and seasonally varying crazy amount of wobble. So the precession rate itself speeds up, slows down, speeds up, slows down, and is pulled differently just across the months. So unlike a top spinning on your desk, right, as it's precessing, it's nice and smooth because it's in a gravity field that's nice and smooth. It's getting a constant torque applied to it. But the Earth, on the other hand, is not getting a constant torque applied to it. It's all over the place. And it gets even crazier. So the moon's position relative to the Earth changes on an 18.6 year cycle. It's called the nodal cycle. And that's because of the lunar orbit's interaction with the sun. The orbit of the moon actually precesses. So at some parts, in some years, the orbit of the moon relative to the Earth is much steeper. And at others, it is more shallow and closer to our actual equator. So here we have, in the shaded area with the blue arrow, that's the direction of our equator and pole. And then the tan plane with the yellow arrow is the ecliptic. That's the plane from the Earth to the sun. And then in green are the different orbits relative to the Earth from the moon. And you can see that in some years, the moon's going to be tilted higher in the sky. In some years, it's going to be tilted lower in the sky. And those extremes are called major and minor standstill. And in fact, we're in a major standstill this year. And we'll look at that more. But because of that, as this relationship between the moon and the Earth changes over this 18.6-year cycle, the torque on the Earth also changes over this 18.6-year cycle. So here I have it plotted for the next 60 years. Here's the lunar declination, and you can see it does oscillate between this major and minor standstill. In the bottom one here, we have our blue is our solar torque that the sun exhibits on the Earth, and then in orange is the lunar torque, and you can see that it varies across here, and then the green's the total. So let's just go ahead and zoom in a bit here, and now you can see as the lunar month's changing, that's our orange line here going up and down, the torque's changing up and down and up and down, and then the sun is more time varying, just 2 lobes per year, and then the green is changing. So this whole situation is torquing the Earth differently throughout this 18-year period, which is actually causing the precession to speed up and slow down throughout this time frame as well, along with all these other extra jitters. So when astronomers have to do really precise ephemeris and calculations of star positions, all this needs to be taken into account. Even the position of the moon across the sky is changing wildly because of this nodal cycle. It's never going to be at the same peak every single full moon for every single time of the year like you would expect it to do if you didn't know that there's this nodal cycle from the moon's orbit changing relative to the Earth. We can kind of plot it a different way so you could really see the differences here. So this is years. Again, we got about 60 years of time, and then the day of the year on the bottom. And then this is going to be the total torque on the Earth, again in units of 10 billion trillion Newton meters. But you can see as the nodal cycle changes, we get areas of more torque on the Earth and areas of less torque on the Earth, and it's very seasonal. And all this is really affecting the Earth in complicated ways, much more complicated than just a top spinning on a desk. And this is going to set us up to discuss in the next video about a big moon stabilizer and theories and thoughts around that as well. But this is helping lay the groundwork of all this complexity as to what's actually going on with the planet that you're living on, instead of just like a top on a table slowly precessing. And I think the vast majority of my viewers currently are astrophotographers, and I said this year we're in a major standstill. So that means the lunar orbit as compared to the Earth is angled as high up as possible. That means our tilt, our axial tilt, is pretty much lined up directly with the tilt of the moon. So that means, for you astrophotographers out there, the winter months, full moon in the northern hemisphere is going to be highest and brightest it's going to be over the next 20 years. which is unfortunate. So I did calculate, if you're at 40-degree latitude, the full moon here, the January full moon, is going to be like 80 degrees in the sky. So almost at the zenith, almost directly overhead. Full moon in the winters during a major standstill, it's just the worst. It's going to be the brightest nights. But you could look forward to 9 years in the future where we're at a minor standstill, where the full moon's not even going to get to 70 degrees overhead. It's going to be like 65 degrees. And it's going to be lower in the horizon, not nearly as bright during the minor standstill for the northern hemisphere. But 2025, unfortunately, is a major standstill year for the nodal cycle. So the January full moon is going to be absolutely the worst to try to get any astrophotography done. And I think this is going to round out the video. I hope this shows you how the Earth is not like a spinning top on a desk where, you know, the gravitational force, it's a constant accelerating reference frame, and it's just going to precess because of that. There's a lot of complexity going on with what is causing the precession of the equinoxes on the planet. It gets into a lot of subtleties that just a spinning top wobbles, so a spinning Earth must wobble, just completely glosses over. And is really going to set us up to understand the next video about a big moon stabilizer, what that really means, and does it really live up to all the hype that so many people claim it to be, or is it possibly based on a really old ensemble study done in the 90s, and there's newer data now? So we're going to get into that next time. I hope this was an eye-opener for a lot of people and showed you a lot of things that maybe you didn't really know what was going on with the planet, and now you should be much more informed. Please comment, like, and subscribe.